record this so that you'll have the information. So if you had a manual, you would have this, but instead I went ahead and posted this for you, but I will encourage you to take notes, because the more ways you can get this into your head, the better. So we are obviously talking about earthquakes today. And do we have to worry about earthquakes in West Virginia? Lacey? Is that something that's on your mind very much? No. Okay, no, not really. But in your manual on page 8.3, it details an enormous earthquake right here in Fairmont. Now, it was back in the early 1900s. And so it was before we had the Richter scale, but it was so violent that chimneys fell down. People were running into the streets screaming. You know, it was felt all over the city. And so the old way to talk about earthquakes was to describe how it affected people. So instead of a Richter scale, which is like, oh, it's a 5.0 on the Richter scale, which gives us a number, this was nobody felt it, would be a 1. And then it was felt by some people in high up buildings, or women would run screaming into the street. Like, it seriously had weird descriptions about how they would determine what you felt. So what causes an earthquake? What causes any earthquake, Aaliyah? That's fair enough. The last time we were on Zoom, I drew too fast, but we were drawing different ways that plates interact. And so one of the ways that plates interact is, let's see here. What's your name?
Hannah.
Tell me one way they can interact.
They can go into each other.
All right. So they can come together or converge. And we'll skip over you. What's another way?
They can separate.
Okay, separate, which we call divergent. Or they diverge, so they divide. Or C, come together. And Dawson, what would be the last way? I'm patient.
Shrink.
Yep.
Transform.
All right. All right. So in your notes, just to remind you of what happens, converge, come together, diverge, separate, transform, slide past. And those are the ways that rocks interact, or that plates interact. You do not have to be on a plate boundary to feel earthquakes. Now that's where you get the big ones, and that's where you get the ones most often. But we in West Virginia, and this will be my West Virginia, so be nice. Anyway, you get the idea. So we have a fault zone down here at the bottom. We do. We have this great big fault zone in Northern Virginia, Southern West Virginia, that it's called the Giles County Fault Zone. That fault zone caused the giant earthquake that was felt in, I'm pretending that that's Fairmont. I'm pretty sure it's close, but I'm eyeballing it. That had to be a pretty big quake in order for chimneys to fall down here in this town. And so it's not that we never get them, they're rare. Because even though we do have fault zones, and that's the biggest one down here at the bottom, it's not something that we think about very often because it doesn't happen very often. The only earthquake I have ever felt here in West Virginia, no, that's a lie, I felt two. One I thought was an explosion, but it was just like a little baby shake. The second one, I was here on third floor in like 2009, 2010, and you could feel it. I thought Dr. Flood was like kicking my chair, but it's the weirdest feeling. It feels like everything is going like this. And I was like, what was in my medicine this morning? Did somebody else feel that? It was crazy. And then
it's more of a worry now in West Virginia with all the fracking.
Fracking only causes smaller ones. And so you will see like Braxton County feels them a lot. And so, yeah, they do cause some earthquakes, but not major ones. So all of earthquakes begin with a force, some kind of tectonic force. And you cannot be afraid to tell me to slow down if I need to. So any force is a push or a pull, some kind of strain. It puts a strain on the rock. And then the rock can respond to that force with stress, and it will either bend slightly or it can break. And that all depends on the strength of the force and the strength of the rock. If it's just a little force, even if it's a weak crust, even if it's a weak part of the crust, it's not going to have that big of a response. But if that force is strong, it'll have a bigger response. So we're going to take a look at the types of stress that are caused during earthquakes. So number one, we have tension stress. Tension stress can be felt mostly in divergent plates. When things are pulling apart, that's called a tension stress. So you pull a rubber band. We pull it and pull it and pull it and pull it. And at some point, it's going to break. You also have compression stress. Which plate boundary would you get compression stress? What was that? Yes, the convergent would have the compression stress, the coming together. And I like to think about this kind of compression stress. How many of you have ever been to the West Virginia Italian Heritage Festival in Clarksburg? All right, there are these two guys, Mel and Ott, and I know one of them has passed, but they would play the accordion. That is compression stress. It comes together and apart like an accordion. Another way to think about that is, if you've ever seen a slinky, if you pull a slinky out on the table and you push it, it compresses all the way through. and that's compression stress. It doesn't rotate. Whoops. There is also a type of compression that does rotate, and we'll get into what kind of wave that is. And when you see that kind of compression, rotational compression, it's like a somersault. So that's the kind of movement. When it talks about a rotation, I think about a somersault. Non-rotation, that's my accordion. And then tension, that's just pulling things apart. So those are our stress types. And then we have 3 different responses to that stress. And so this is how the crust can respond. We can have an elastic response. We can have a plastic response, or we can have a brittle response. And I wish it was non-pandemic time so you guys could hold hands, and it's a lot easier to see these things. So if you have an elastic response, it temporarily deforms the material. It's like the rubber band. You pull and pull and pull. If you don't break the rubber band and you let it go, what happens? Okay, it goes flying. If I pick up the rubber band, is it going to look any different? No. So elastic means it goes back to its initial shape. Plastic is a little different. A plastic response is what happens when the rock gets super heated and is still undergoing stress. It bends. The rock will bend. So a good place to think about when I talk about that plastic deformation, if you're heading to Washington, D.C. and you're out on 68 and you drive by these rocks, let me make sure this is dry erase, and those rocks look like this. Does anybody know what I'm talking about? Next time you go to DC, look for that. It's on Sidling Hill. And when you drive by, all of the rocks look like a big smiley face as you drive through. In fact, I'm going to try. Let me pause with that share and find a picture of that for you. This is in Maryland. Of course, there's not a big picture. Hold on a second. Oh, there's a good picture of it. All right. So you see the bend in these rocks. That is from that compression force. Actually, it's from Proto-Africa and Proto-North America coming together roughly 300 and some million years ago. And so this had a plastic response. Didn't really break, but it bent. It never went back to the same shape. So that's what plastic is. It doesn't go back to the same shape. And then, of course, we have brittle. And a brittle response means the rock breaks and forms a fault. A break in a rock, and we're talking like big breaks, big rocks, is called a fault. Do you guys have any questions about that so far? It's pretty straightforward. All right. So elastic strain, or the elastic response. The force is applied, and the object changes shape, but the energy is stored. Because remember, it's only going to change shape a little bit. I mean, temporarily change shape. Because once you release the force, it turns back into its original shape. So this is the whole idea behind stretching a rubber band, letting it go, picking it up. It's the same shape, same rubber band shape as it was before. That stored energy, when it is released, we call it work. So that's like a physics term. When energy is released, it's referred to as work. Okay. So where in geology will we find examples of this? You know, because we are not studying rubber bands. So during the Ice Age, we had glaciers that came down about 10 miles north of the northern panhandle of West Virginia. They never got into West Virginia, but they got about 10 miles away. And those glaciers were so giant and heavy, they like pushed down on the North American plate. And so they weighed it down. And so it would bow under the weight of that glacier. Well, what eventually happens to glaciers? What do? Yeah, they eventually melt. As the weight of the glacier subsided, the crust basically was like, oh, get off of me. And it like kind of bounces back into place. Not really bounce because, you know, we're talking about thousands and thousands of years. But in geology, bounces back into place. And so we have something called rebound. It just goes back to its original shape. In geology, this also happens with the mountains. So the Appalachian Mountains are some of the oldest mountains in the world. They formed at the same time Pangea formed, to like put that in perspective. Our mountains formed before the dinosaurs ever walked the earth. That's why we don't have any dinosaur fossils in West Virginia. Our rocks are too old for dinosaurs. Like, that's amazing. But, so here we have these giant mountains. At one time, they were as large or larger than the Himalayan mountains. So when you think about something like Spruce Knob, add another mile up to it. That's how large our mountains were. Mountains don't just form above the crust. Mountains also have like roots. And so when Africa pushed these mountains up on the North American plate, it also pushed stuff down. So these are mountains. And this is like the crust. And then down below the crust, we have kind of like the roots of the mountains. And then what's underneath of here? What's underneath the crust is the mantle. Okay. So what happens to mountains over the years? They don't melt, but what do? And I think we are back up front.
They erode.
They do. They erode away. So they're losing some weight off the top. So what's going to happen? In all honesty, our mountains have been eroding for 300 million years. Wouldn't you imagine that they'd be flat? I mean, that's a long time to erode. But this part, as this erodes off the top, this pushes up. And so until we are out of mountain roots, our mountains are still going to stay pretty large. And this is called isostatic rebound. Right here. Isostatic rebound is just a fancy term for you lose weight off the top and the bottom pushes up to maintain a shape. And that's what is happening in the Appalachian Mountains. As they have eroded over the last 300 million years, the bottoms have been pushed up because the mantle is liquid and it is pushing to make more room. All right, so let's talk about plastic strain. So isostatic rebound is a form of elastic strain to keep the shape of the crust the same. Plastic strain is a little bit different. The force is applied and the energy is consumed or used. And what is it used for? It's used to form a different shape. So even once the force is no longer being applied, it changed its shape permanently. The word plastic is a little bit different in geology. Plastic, I want you to think about a rock behaving as not quite a liquid, but it's like a rock that behaves kind of like rubber. It bends because it gets so hot, but it doesn't quite melt. And so that's kind of what we think about as plastic. The top of the mantle where it meets the crust, it's still rocky, but it bends. It's got this plastic deformation. So here is an example of plastic deformation. You can see how the rocks are completely bent. I wish you would have told me where this was. It almost looks like Maine. But anyway, it doesn't matter where it is. Rocks will happen like this. We have parts of West Virginia where the rock has been so deformed, you can't tell which way was originally the top or the bottom of it. It's been so deformed. And then, which brings us to brittle. Easiest way for me to remember with brittle breaks, BR. When I started my doctoral program, I was ejected from a car and run over. And so we had lots of memory problems going on in this head for quite some time. And so if I tell you ways to remember things, it got me through my doctoral program. So those are ways that I had to learn. So I'm more than happy to help you guys think of ways to remember these things because it's a lot to remember. So energy that's stored up has a limit, just like with that rubber band. You can't stretch a rubber band forever. There's a limit to how much force you can apply and how much energy can be stored. So once you stretch it so far that you exceed the material's ability to store the energy, it snaps and the object breaks. Whoops. And then all of that stored energy is then released. When that is released, we feel earthquakes. That's where you get faults. So these two sections used to line up. This lined up with this here. And everything was perfect. And then we had an applied force, probably 2 plates colliding, and it broke. And it moved this top portion down the slope. So when we talk about faults, we're talking about giant cracks in the rock. You can see right here, if these people are 6 feet tall, this is a large fault line. And I did not bring a bit of honey to you today. So I will be right back because I do have some Play-Doh. So hang on for a second.
Yeah. Yes.
No, I'm here. I'm here 5 weeks or so. It's not. Not too bad. I was really worried about it. That was good though. Yeah, it was only like 4 or 5 days.
When I lost my phone case, I was down about this so much.
I was not. And like, I was just so happy all the time. And then after, like, I didn't feel like my face was strong. Yeah. It's not just around the ear. I was trying to have my finger and shake my leg. It's disgusting. I ate so much. I felt horrible. Listening last week. I slept like 2 hours and I was sick.
Yeah.
And then I couldn't really sleep again. I was like,
Yeah.
brushing my teeth and home. Did you go to school? Yeah, not a transfer here too. What?
No, she
Only lay on back and forth for a while.
transferring the next semester. But right now she's like back home.
Everybody's showing the babies. It is. Yeah.
I
No.
know.
He's picking up from Fairmont. I don't even know how many times. But she's not very
Good. He hasn't worked for a while. No, he's a guy now. But
All right, sorry.
his dad lives up too. Last, I think like a week before last, they went to Indiana for a week. And it didn't work last week or this week. And then he goes back next week.
Okay, so everybody can come and get their own either clay or Play-Doh.
Sorry. like, I had a fever and it was awful.
All right. So once you get your Play-Doh out, I want you to try to replicate what happens when the strength of the material is exceeded. So the first response is going to be elastic. You can dig it out with your pencil if you want. You want to protect those nails. There's clay back there. All right. So what are you doing right now? Okay. How do you do that?
I don't know.
First thing we're going to do is start to pull. But I want you to pull only until just before it reaches its limit, or just when you think it's about to reach its limit. Okay, so you're probably good.
Mine's at the middle stage.
Oh, yeah, you're good. I'll try to just hold still.
I know. Very
Good.
close to reach.
It's not. That's stressing me.
That's not good.
That's as far as I want to go.
Oh, you're pretty dry.
Oh, yeah. It's
Yeah.
so dry.
I don't know the last time Deb and I replaced this. All right. So if you were to let it go, is it going to retain its shape or stay put? So is it elastic, plastic, or brittle? It is a plastic deformation. If you went beyond that force, that would be brittle. All right. So in an earthquake, what you just did kind of happens in an earthquake as well. They're storing that energy. These rocks are storing the energy until it finally breaks and the energy is released. So what kind of energy are they storing? They're storing elastic energy. Once they reach their elastic limit, the rock slips. So with a partner, I want you to take your Play-Doh again, and you can just roll it into a couple of balls. If you don't have a partner, you can roll 2 balls of Play-Doh. And I just want you to push them against each other until something happens. Just keep pushing, pushing, pushing. Push harder.
Yours was stronger than mine.
Okay. anybody have Play-Doh, like one went on top of the other?
No.
Okay. That was my next question. Do we have any plastic deformation where they smushed together and then made a different shape? That's what mostly everybody should be. And what kind of force were we using with that? Convergent, good. So a convergent force, they're coming together.
They're still very close. Okay.
So, whoops. If we had two different densities of Play-Doh, like maybe Play-Doh and clay, or Play-Doh in a real rock, the Play-Doh is going to go on top as you push it together. It'll go on top and the clay will stay at the bottom, or the rock will stay at the bottom. But on the earth, it's similar. Something is going to slip eventually. And all of that buildup energy is released. And then you get something like that, where the energy has to travel. The energy can't stay still. And it travels through the earth. And then we feel it as an earthquake. So 2 things I want you to get out of this is, you can put your Play-Doh away, is the focus is where that rock breaks and the energy is released underground. The focus is exactly where the break in the rock happens, or the break in the crust. The epicenter is the point directly above the focus. It's on the surface. This is where we collect data, or the distance from the epicenter. And that's the only difference. The focus is where the rock actually breaks. The epicenter is directly above it on the surface of the earth. So how do we measure how bad an earthquake is? Well, I'm going to post this article on the Fairmont earthquake. And we are going to use the modified Mercalli scale, which I will also post what that is. And it's just a description of what was happening. So as you read the newspaper article, if you see, oh, people ran into the street, then you look at the modified Mercalli scale and say, okay, where does it say that people ran into the street? And that is how you judge how strong an earthquake is on that old scale. And so the modified Mercalli scale is just a descriptive way of talking to people about the intensity of the earthquake. It was way before we had the Richter scale. And using the modified Mercalli, they drew these lines. It's basically like, I don't know, like connect the dots. You look for all of the 3s, then you draw a circle around those, and all of the 4s and all of the 5s. And we will see that this one, our focus would have been right in the middle. You are not going to have to do this. Just We don't have all of the books. We don't have them with us. This is also not very true. I do want you to read your little earthquake book, just that little children's book that you have. We are going to be meeting in here one more time, and I'm going to have a Nearpod lesson for you, which means I want you to bring some kind of device. You can use your phone, but it doesn't always work as well on a phone as it does to have like a laptop or a tablet or an iPad, something. So if all you have is your phone, that's okay, like if you forget. But please try to bring something with you. Earthquake mapping is fine. Let me ask you guys questions real quick about, let me stop this.